Hello. I hope you're doing well. Monday Dance Max back here with physics. This time I am focusing now on A level physics, paper 1. This is section B. I'll be making videos about different sections, but always observe how I label them. So section B deals with the heat, as you all know very well. And this is the very first video. I'm calling it lesson 1. So I have labeled it B001. That is section B and the first video. Now, in this topic of heat, we start with the subtopics. This branch here, we look at different subtopics. So we have thermometry, introducing the thermometric properties of matter. The thermal properties, not thermometric, but thermal properties of matter. So thermometry. Under thermometry, we explore thermometric properties. We look at temperature scales, look at different thermometers and their comparisons. So the general terms that we use in thermometry, like you've heard them before, even from primary and O level. The first one is heat. So you may be asked to define heat. Simply, we define heat as a form of energy which flows from one point to another due to the temperature difference between the 2 points. So it's a form of energy. And it always flows from one point to another, or you can say from one region to another. From one region to another. But basically, the two regions or the 2 points have to be at different temperatures. And you know very well that heat will flow from a region or a point that is at a higher temperature to that which is at a lower temperature. Now the SI unit of heat, like all other forms of energy, is the joule. It is the joule, abbreviated as capital J. So the second term that you have to know, like you've heard before, is what we call temperature. Temperature. What is temperature? Temperature is defined as the degree of hotness or coldness of an object. Actually, in other books, they will say is the measure of the internal energy, the thermal energy of an object. But here we're just saying simply that temperature is the degree of hotness or coldness of an object. And the SI unit of temperature is the Kelvin. Please note that the SI unit of temperature is the Kelvin. This Kelvin, not degrees Celsius, and not centigrade, not degrees Fahrenheit, but the Kelvin. If you're writing the word, you start with a small k, but the abbreviation is by a capital K. The other commonly used units are the degrees Celsius. So these are just other commonly used units when we're dealing with temperatures. So we have degrees Celsius, and we can easily convert from Kelvin to degrees Celsius and even vice versa, from degrees Celsius to Kelvin. So if you want to change from degrees Celsius to Kelvin, you add 273. An example is if you have 27 degrees Celsius and you want to convert to Kelvin, you add the 27 plus 273. So you're going to end up with, here simply, you end up with 300 Kelvin. All right. Now, because we have talked about the Kelvin and the degrees Celsius, so we are going to deal with basically two scales of temperature. And the first one is what we call the Celsius scale. Observe that every time I write Celsius, I am writing starting with the capital C. Capital C, please note that. And here you write an S, not a C. So we have basically the Celsius scale and the thermodynamic scale. The thermodynamic scale is sometimes called the absolute temperature scale. The absolute temperature scale, or the Kelvin scale. It's what we call the thermodynamic scale. Let us look at number 3, the other term among the terms that we use under the thermometry. So we have what we call the thermometric properties. I want you to pay close attention to this part. because you don't cover this at O level in details. You don't. So thermometric properties. Thermometric properties. So what do we mean by thermometric properties? Now, a thermometric property is the physical property of a substance whose value changes linearly and continuously with changing temperature. Or you can just say a thermometric property is a physical property of a substance whose value changes linearly. The value must change linearly. If you don't use the word linearly, you can say uniformly. Uniformly and continuously with the temperature. Whether you put changing temperature, as long as you've talked about the value of this substance or the value of this physical quantity. Actually, we are calling it a physical property, or you can call it a physical quantity whose value changes linearly and continuously with the changing temperature. That's what we call a thermometric property. A physical quantity or a physical property of a substance whose value changes linearly and continuously. You can say uniformly and continuously with the temperature or with changing temperature. That is what we call the thermometric property. Okay, now I want us to look at the examples of thermometric properties. There are around 6, or for now I think I can just give you the 5. The sixth one I'll give you as we shall be exploring the types of thermometers. So the first one is the electrical resistance of a wire. Do me a favor and put an A here. Electrical resistance of a wire, and in most cases look at a platinum wire. So the pressure of a fixed mass of a gas at constant volume. This is called, this is always for a constant volume gas thermometer. So now, let me take you back a little bit. We are saying that a thermometric property is the property of a substance whose value changes, which value varies or changes uniformly and continuously with the temperature. You know very well that the electrical resistance of a wire, if you take platinum for example, will increase as the temperature increases, and it will increase uniformly and continuously. So that means the electrical resistance of a wire qualifies to be a thermometric property. Please note that I'm not asking for the thermometric substance. Here the thermometric substance is the wire, the platinum wire, but the thermometric property is the electrical resistance of that wire. In number 2, we are looking at the pressure of a fixed mass of a gas at constant volume, the pressure. So when you increase the pressure of that fixed mass of a gas, when you increase the temperature, when you increase the temperature, definitely the pressure will increase. Number 3, the volume of a fixed mass of a gas at constant pressure. Now I just reversed the second one. Where there was pressure, I put volume and came up with a new one. So you can decide now to see exactly what happens to the volume if I keep changing the pressure. What happens to the volume at constant pressure? I maintain the pressure constant, but I keep changing the temperature. What will happen to the volume? Definitely, the volume of the fixed mass of the gas at constant pressure will keep changing. So number 4 is what we call the EMF of a thermocouple. We shall look at a thermocouple just I think in the third lesson. Electromotive force of a thermocouple. Number 5 is the length of a mercury column in a capillary tube. Number 5 is used for what we call, by the way, here you can say length of a liquid column in a capillary tube, because here we can use either mercury or even alcohol. It can still work. Okay, now what are the characteristics of a thermometric property? For a physical quantity to qualify to be a thermometric property, what special features should it have? Number one, that thermometric property should vary continuously with the temperature. It should vary continuously with the temperature. Next, it should vary linearly with the change in temperature, or should vary or change linearly with the change in temperature. The first point was continuously. It should not vary and then stop varying. It should vary continuously. Then here it should vary uniformly, varying uniformly, or what we call linearly with the change in temperature. And then it should be sensitive to temperature changes. It should be sensitive to temperature changes. Do me a favor and put an S here. Or to temperature change anyway. I.e. it should change considerably for small temperature changes. So if there is just a slight temperature change, then even that thermometric property should also change considerably. So it should be accurately measurable. It should be one that you can easily measure with a simple apparatus. And then it should be measurable over a wide range of temperatures. So a good thermometric property should possess these characteristics for it to qualify to be a good thermometric property. Here, I want you to try to find out why isn't the length of water in a capillary tube, why don't we use it as a thermometric property? Or in other terms, let me just simplify it better. Why don't we use water as a thermometric liquid? We shall later look at thermometric liquids. But I'm asking, why don't we use water? What doesn't it do? What doesn't it do? Among these, if you look at these properties, they are characteristics of a good thermometric property, but they come in line with the thermometric substance. Oh my god. You people, English is not easy, but you'll pardon me. Sometimes I feel like talking in my mother tongue. Alright, so we are saying that a good thermometric property should possess these features. Now, number four, among the terms that we use in thermometry are what we call the fixed points. So we have fixed points. A fixed point is a temperature. It's not a point, it's a temperature at which a particular physical change is expected to take place. Please note that a fixed point is a temperature at which a particular physical change is expected to occur. So there are three fixed points, namely we have the ice point. In many books it's called the lower fixed point, the steam point, which is also called the upper fixed point, and then we have the triple point of water, Now the first two, the ice point and the steam point, these two are used when we are defining a Celsius scale, when we are determining a Celsius scale. And then the triple point of water, for it, it's used when we are defining or determining a Kelvin scale or a thermodynamic scale. Now, by definition, the ice point or the lower fixed point is the temperature of pure melting ice. The temperature of pure melting ice. Now, for ice, you know very well that if the melting of the ice doesn't really so much depend on the atmospheric pressure. So, whether someone says that the lower fixed point of the ice point is the temperature of pure melting ice at standard atmospheric pressure, or even if they leave out the standard atmospheric pressure part, still they are right. It will be marked right. So next is what we call the steam point, or you can call it the upper fixed point. The upper fixed point is the temperature of steam at standard atmospheric pressure. The temperature of steam at standard atmospheric pressure. And then lastly, we have what we call the triple point of water. For your information, if you're defining the steam point or the upper fixed point, you can also call it the temperature of pure boiling water. Pure boiling water at standard atmospheric pressure, but we prefer using the steam. Then the triple point of water is quite interesting. The triple point of water is a temperature at which pure ice, pure water, and pure water vapor coexist in dynamic equilibrium. Very interesting. How can we have pure ice, pure water, and pure water vapor, all the three states of matter of water existing together in dynamic equilibrium? So at the temperature at which that occurs is what we call the triple point of water. And please, we only look at the triple point of water. We have what we call a triple point cell. A triple point cell. I'm going to illustrate just a little bit to show you in a video that this is possible. But I want you to see that in a triple point cell, we have water vapor here, we have ice formed here, and we have water. And all the three, if you put a gas thermometer here or in a thermometer, you'll find that the three, that if this is established, as long as there is equilibrium established, the temperature reading for this kind of cell is going to be constant. And this side here is a point where we can connect. We just pour water here, and then we connect externally here to a vacuum pump. Then we pump out the air to reduce the pressure. Inside, and once you reduce the pressure, you will see that the water will start boiling. And then at one point there will be ice formed, water there, and even the water vapor. That temperature is what we call the triple point of water, and it corresponds to about 0.01 degrees Celsius or 273.16. That is the triple point of water. Alright, now how do we establish a Celsius scale, or what we call the centigrade scale, as some books still call it, the old version? Establishing a Celsius scale or the temperature scale. For you to establish any scale, the first thing you have to obtain is a thermometric property. So you have to decide, am I using the electrical resistance of a platinum wire? Am I using the EMF of a thermocouple? Am I using the length of a mercury column in a capillary tube? So you first obtain a thermometric property. Number two, you measure the value of the thermometric property at the ice point. So you get the value of the thermometric property at the ice point. That value we are calling it X naught. Why are we saying naught? Because at that temperature we're looking at 0. Next, we measure the value of the thermometric property. If it's, for example, the length of a mercury column. So you measure the value of the thermometric property at steam point, and we call that X100. So the property we are using is X. We don't know it. We just took an arbitrary letter X. So you measure the value of the thermometric property at the steam point, call it X100. Then measure finally, or second last step, you measure the value of the thermometric property now at the unknown temperature theta. And then, so the value of the temperature, which we are calling theta, is then calculated from the expression. The expression is this: theta equals to x theta minus x naught over x100 minus x naught times 100 degrees Celsius. Okay, now x100 minus x naught is what we call the fundamental interval. If by definition the fundamental interval is the difference between the value of a thermometric property at the upper fixed point and its value at the lower fixed point. So we are saying the difference, subtraction, between the value of that thermometric property at the upper fixed point and the value of that thermometric property at the lower fixed point. So now, how do we establish a Kelvin scale of temperature? How do we establish a Kelvin scale of temperature? For Kelvin scale of temperature, you have to understand that the Kelvin scale has only one fixed point, which we call the triple point of water, and it is at 273.16 Kelvin. So to obtain to establish a Kelvin scale, just like we did for a Celsius scale, start by obtaining a thermometric property, say X. Then find the value of the thermometric property at the triple point of water. That is done just by, if for example you're using a constant volume gas thermometer, get that bulb and insert it in what we call the triple point cell. So next, you find the value of the thermometric property at the unknown temperature, say xt. Now I'm calling it xt. Then check the other, this one I call it xtr. Tr because I'm looking at the triple point of water, and then here I'm calling the temperature capital T. So we are saying that find the value of that thermometric property at the unknown temperature, say xt. And then finally, the unknown temperature T is then calculated from the expression. Please note these two expressions properly. The first one, we use the theta for the Celsius scale. Now for the thermodynamic scale or the Kelvin scale, we are using xt. We are using T capital T instead of theta, equals to xt over xtr. That is the value of the thermometric property at that temperature over the value of the thermometric property at the triple point of water times 273.16 Kelvin. Now observe that this temperature capital T has to be in Kelvin, not degrees Celsius, but Kelvin. Okay, now I just want to close this up by us looking at a few questions here. There is question number 1 here. It says the resistance of a platinum thermometer. The resistances of a platinum thermometer are 5.7 ohms, 5.5 ohms, and 5.2 ohms at the steam point at an unknown temperature. We don't know it. And the ice point respectively. Determine the unknown temperature on the thermodynamic scale. Okay, so we're going to do this together. I want you to follow through. We do this together. So we are saying, they told us that the resistance of a platinum thermometer, the resistance at, they started by steam point. So let us call that R 100. Now, let us call the value at the steam point. Let's call it R 100. We call it R 100. So we will say that R 100 equals to, they gave it to us as 5.7 ohms. Then if you follow through, at the unknown temperature it's 5.5. So we say the unknown temperature is theta. The resistance, that is R theta, equals to 5.5 ohms. And then the resistance at the ice point, which is R naught, equals to, that was 5.2 ohms. Now the question says, determine the unknown temperature on the thermodynamic scale. So let's start by getting, if you remember very well, we were told that if you have theta, you want to get theta on the Celsius scale, we shall later convert. The formula is R, that value. Now this time we can't say X, but because we know it's a resistance, so we say R theta minus R naught over R 100 minus R naught. Then the whole thing we multiply by 100 degrees Celsius. So we are going to end up with, what is R theta? The resistance at the unknown temperature is given as 5.5 minus the resistance at the ice point is 5.2 divided by the resistance at 100 or at the steam point is 5.7 minus the resistance at the ice point, which is 5.2. Then whatever we get here, we multiply everything by 100 degrees Celsius. So we're going to end up with up is 0.3 over 0.5 times 100 degrees Celsius, and this kindly and simply give us, this gives us 60 degrees Celsius. But the question said, determine the unknown temperature on the thermodynamic scale. So on the thermodynamic scale, we know that T, the temperature capital T, should be equal to, you get the theta in degrees Celsius plus 273. So let us add. We are going to have our 60 plus 273, and whatever we get should be in Kelvin, by the way, Kelvin, and we end up with 333 Kelvin. 333 Kelvin. Therefore we can conclude and say that okay, I wanted to have all our answers shown, everything here. Okay, so we can conclude and say that the temperature on the thermodynamic scale is 333 Kelvin. You can write that conclusion. Next, the next number says the resistance of an element of a platinum resistance thermometer is 4 ohms at ice point and 5.46 ohms at the steam point. What temperature on the platinum resistance scale would correspond to a resistance of 9.48 ohms? This is your question. Number 2 is yours. Please, you do it. I'm waiting for the answer. Thank you. Now I'm going to do number 3 instead. We're going to do number 3 together. So number 3 says number 3 says the resistance of a platinum wire, the resistance of platinum at the triple point of water is 85 ohms. Okay, so we can write this and say we were told that the resistance at the triple point, I'm writing it as RTR, resistance at triple point, is given as 85 ohms. Okay, they told us, the question is, what will be the resistance of the platinum wire at 110 degrees Celsius? So they gave us a temperature, but remember, when they talk about triple point, so they're asking us the resistance at that temperature T, capital T. Okay, but they gave us the temperature. So what we do is, let's first get the value of T. Remember, T is equal to theta plus 273. So we shall get 110 plus 273. And what does this give us? This kindly and simply gives us 383 Kelvin. I hope I'm right. Yeah, 1 plus 2 is 3, then 8 and the 3. Yes, that's it. Then remember our formula. If we know the formula, life becomes easy. We were told that T equals to, you get that thermometric property at that temperature you're looking for over the thermometric property, which is now for us using the resistance over RTR, then the whole thing you multiply by 273.16, and what you get will be in Kelvin. Okay, now the question here asked, they said what would be the resistance of the platinum wire. So they're asking for RT, so let's substitute. A capital T, which is the temperature, is 383. 383 should be equal to, please observe this, don't write, if you're dealing with a triple point of water, anywhere, and then you write in degrees Celsius, you will be off. The temperature T has to be in Kelvin. So 383 should be equal to RT, we are looking for RT, over RTR, the resistance at the triple point is 85 ohms, times 273, come on, 0.16. Okay, then simply we want to make RT the subject. RT is going to be 383 times 85 divided by 273.16, and whatever we get will be in ohms. I am ending up with 119.179, you can say 18 ohms. Ohms. So let me try to make this visible so that people can see what we've been doing. Alright, yeah, that marks the end of number 3. Now I have some more few questions for you. These questions will serve as an introduction to the next lesson. Questions for you.